Okay, so today we have this pretty cool integral, and this is the integral of the natural log of 2024 plus tan square x from 0 to pi by 2. And we're going to solve it using Feynman's trick. If you don't know what that is, we're going to basically set up a function. Let's call it I of alpha, and it's going to be the integral from 0 to pi by 2 of the natural log of alpha plus tan square x dx. And what you notice is that if we plug in 2024 is alpha into this, we get our original integral back. So what that means is that this integral is actually equal to I of 2024. So what we can do with this information is we can differentiate both sides of this equation. So we can take d by d alpha, I of alpha is going to be equal to the integral from 0 to pi by 2 and the derivative of this part. And so we have I dash of alpha is going to be equal to the integral from 0 to pi by 2 of 1 by alpha plus tan square x. And this was so easy because it's with respect to alpha, so the tan square x doesn't make it more difficult or anything. So what we can do now is we can simplify this integral because it's actually a pretty basic integral. So I'm going to solve the indefinite integral from 0, actually sorry, the indefinite integral with no bounds of 1 by alpha plus tan square x dx. And I'm going to make a u sub, so that u sub is going to be u is equal to tan x, and so we have dx is equal to du by sec square x. So what that means is that this integral is equal to the integral of 1 by alpha plus u square, and then here we have 1 by sec square x du. And what's interesting about this is that sec square x is actually equal to 1 plus tan square x. So this will be equal to the integral of 1 by alpha plus u square. And then tan square x plus 1, since tan x is u square plus 1 with respect to u. So we can use linear partial fractions to decompose this. And this will become the integral of 1 by alpha minus 1 u square plus 1 minus 1 by alpha minus 1 u square plus alpha du. So now these are two pretty well-known integrals if we just factor out the 1 by alpha minus 1. So once we factor it out, this is going to become 1 by alpha minus 1. Yeah, sorry, 1 by alpha minus 1 of the integral of 1 by u square plus 1 plus the integral of 1 by u square plus alpha. And these are two pretty well-known integrals which I'm pretty sure most of you know. So this is the arctan integral, and this is a variation of the arctan integral. So it's going to be 1 by alpha minus 1, and then the integral of 1 by u square plus 1 is arctan u. So arctan u. And for this one, we just have to make the u sub, or I guess we already used u, so the j sub, and we let j or t equal to 1 by root alpha. So, oh wait, actually, that's my bad. I miscopied the negative sign here, so it becomes negative from here. So, all we have to make is a substitution t is equal to 1 by root alpha, and we get arctan u by root alpha, and then in the denominator, we get root alpha. and we've simplified this. So this is now I dash, yeah, I dash of alpha. So once again, we found I dash of alpha is this integral, and we solved the indefinite integral. So this is our indefinite integral in terms of u. And just remember that we made this out of u is equal to tan x. So now we can just put tan x back instead of u, and the arctan of tan x is x, and it's the same thing here. You can try with limits, um, and it's going to be the same thing. So now we can just apply bounds to this expression, so pi by 2 and 0, since those were the bounds of our original integral, and we can sub x in, and we can sub tan x in place of u, since that's the substitution we made in the beginning. So this is going to be equal to 1 by alpha minus 1 of, well, arctan of tan x is just x, so pi by 2 minus, and then you can take the limits, but essentially the same thing happens here. So we have pi by 2 by, yeah, it's too big, just 1 second, pi by 2 by root alpha, and we also have to plug in 0. But the thing is, x, as if we plug in 0, then we already have x in both of the numerators, and so what that means is that the entire thing is just going to be 0, so we don't need to bother with that. So this is our new um, result. So what that means is that the integral from 0 to pi by 2 of 1 by alpha plus tan square x is equal to this. And so we've solved this initial question that we had here. And now what we're going to do is, it seems kind of counterintuitive, but we're going to integrate both sides again, since we now have them in different forms. So we're going to take the integral of I dash of alpha. Maybe I should write it a little bit down. So yeah, the integral of I dash of alpha d alpha is going to be equal to the integral of 1 by alpha minus 1 pi by 2 minus pi by 2 by root alpha d alpha. So this is going to be I of alpha, and this will be the integral of pi by 2 by alpha minus 1 minus pi by 2 by root alpha, then alpha minus 1. So we can just factor the pi by 2 out. So we have I of alpha is equal to pi by 2 times the integral of 1 by alpha minus 1 minus 1 by alpha minus 1. And again, these are two really common integrals, and for this you can make a t sub if you're unfamiliar with it, but this is again a really common integral. So now we have I of alpha equal to pi by 2, and then this is going to be log alpha minus 1, and then minus log of root alpha plus 1 by root alpha minus 1. So that's our I of alpha. And now if we go back to our original question, you'll notice that our original integral is actually equal to I of alpha when alpha is equal to 2024. So since we found it in such a nice um, expressible form, we just have to plug in 2024 again into this expression. So what that means is we're going to have, well, first of all, let's just simplify this expression in general. This is going to be pi of log alpha plus 1. So now we just have to plug in alpha. So this is going to be equal to pi log 2024 5. Oh, sorry, my bad. This should be root alpha plus 1. Algebra. Root alpha plus 1. So this should be equal to pi log root 2024 plus 1. And here we have our final solution.